Hello everyone, I'm Jesse Mason, and for this episode of Teach Me, we'll determine the cost of heating an outdoor pool. This problem was inspired by my wife, who asked me one Saturday morning in September, "What do you think it costs to heat Grandpa's pool for one last swim?" As always, I said to her, grabbing a Sharpie, we begin by drawing a picture. So here's our cylindrical pool of diameter D, and it's filled with water to some depth H. And that's all we need for our picture. Now we'll list our knowns and unknowns, beginning with dimensions. Diameter we'll say is 7 meters, and depth of water, let's go with 1.3 meters. Now, the initial temperature of the water is about that of the surrounding air, which on the mid-September day in question was a chilly 55 degrees Fahrenheit. That works out to be about 13 degrees Celsius. To make it a comfortable swim, we'll heat the water to 27 degrees Celsius, which is about 80 degrees Fahrenheit. Last, we'll list our ultimate unknown, which is the cost, uppercase C, of changing the water's temperature. Now we select an equation to solve the problem. Well, we don't have a single equation for this exact problem, but we can cobble something together using what we know about thermodynamics and commerce. This problem is all about energy. We've got a substance that undergoes no phase change, but changes temperature. The energy required for this is given by Q equals mc delta T, where m is the mass of the substance, c is the specific heat of the substance, and delta T is, of course, the temperature change. Now, if we were attempting one last swim in, say, December, when the water would start out frozen, then we'd have a phase change, and our equation would require two additional terms, one to account for the energy required to melt the ice, and another to account for the energy required to bring the ice's temperature up to the melting point. Okay, back to September. We need a value for specific heat, which is kind of like a substance-specific thermal inertia. Water, as it turns out, has an incredibly high specific heat, 4,186 joules per kilogram degree Celsius, which means that it can absorb huge quantities of energy relative to its temperature change. So we've got C, what about M? Well, we're not given mass directly, but we can calculate mass using water's density and its volume. In this problem, the water is in the shape of a cylinder, so its volume can be written as pi times r squared times h. The only value we need now is water's density, and it's a gimme. 1,000 kilograms per cubic meter. Now we insert our values. Water's density times pi times 3.5 meters squared, that's our radius, times a depth of 1.3 meters, times water's specific heat, times 27 degrees minus 13 degrees. Multiplying, we get 2,932,000,000, or 2,932 megajoules. I know, that looks like a decimal mark, but I assure you that it's a comma. Okay, now we know how much energy we need to heat the pool. To determine the energy bill for heating the pool, we simply multiply the price per unit energy by the energy we're going to use, and that will give us the heating cost. The price of energy here in Detroit, according to my most recent electric bill, is 8 cents per kilowatt hour. Now, the energy required to heat the pool is in the more familiar energy units of joules, so we'll convert our price of energy units presently. First, we'll multiply by kilowatts over 1,000 watts. Kilowatts divide out. Then we'll multiply by watts over joules per second. That's the definition of the watt. Watts divide out. And lastly, we'll convert hours into seconds, and our time units divide out, which means that 8 cents buys us 3,600,000, or 3.6 megajoules. Cool. So we insert our values into the energy bill equation, 8 cents over 3.6 megajoules times 2,932 megajoules, and we discover that it will cost a whopping 65 bones to swim in September. And this makes sense given water's high specific heat. Now, I should point out that this is what it would cost to heat a pool in physics land. But in the real world, water heaters aren't 100% efficient, and the environment, that is to say the air above and the pool itself, leaches thermal energy from the water when there's a temperature difference. And the more drastic the difference, the more drastic the thermal loss. Oh, and we're completely neglecting the electricity required to run the water pump. So let's tack an extra, let's say $15 on there to account for these things, which means that one last swim at Grandpa's cost as much as a visit to a water park. Now, before we wrap up here, let's revisit our work and come up with an equation that the average Joe can use to determine pool heating costs, just for funsies. Starting from the energy bill equation, we'll combine constants via multiplication. From the price of energy, we'll take the unit conversion. From the heat equation, we'll take the specific heat and density of water. And multiplying these together gives us one all-encompassing pool heating cost determination constant, which yields C, the cost of heating the pool, equals 1.163, that's our constant, times P times V times delta T, where P is the price of energy in dollars or cents per kilowatt hour, V is the water volume in cubic meters, and delta T is the change in water temperature in degrees Celsius. And there you go, a nice little equation to talk someone out of heating a pool off-season. It didn't work for me. We still fired it up for one last dip. YOLO, baby! I'm Jesse Mason, and I hope you found this video helpful. If you have a suggestion for future Teach Me videos, or just want to say hello from your part of the world, please do so in the comments section below. And as always, happy learning.